All right, let's go over some typical scale factor dilation similarity type problems. Okay, so this first one. Question first is, are they similar? So I'm asking, is like triangle GEO similar to ALM? And well, one of the ways we can prove similarity is looking at side, side, side. So let's look at side, side, side. And if we can show that all three sides have the same proportionality constant or the same ratio or the same scale factor, then we know the two triangles are similar. And if they're similar, then we can write a similarity statement. So we want to look at these ratios. So let's look at 10 to 16. And 10 to 16 is a 1.6 ratio, meaning 16 is 1.6 times bigger than 10. Let's look at 12.8 to 8, and that will also turn out to be 1.6. And then let's look at 19.2 over 12, which is also 1.6. So what we've shown here is that all three sides here are 1.6 times bigger than here. Again, that's how you find the scale factor. You look at the ratio, meaning the division of the two sides. And so 1.6 bigger, 1.6 bigger, 1.6 bigger, so that we actually do have a side, side, side similarity thing. So are they similar? Yes. If they're similar, write a similarity statement. So let's say triangle GEO is similar to triangle, and we have to get this correct. So we went medium, small, large. Now medium, small, large. We got to go around the same way. So ALM. ALM. Does that make sense? So yes, they're similar. Why? Because we've shown that all three sides, all three corresponding sides, have the exact same scale factor. We find the scale factor by looking at the ratio of the sides. And then we wrote a similarity statement and said, and we were particular about the order. We went GEO. This order didn't matter. We could have started anywhere we wanted, but once you do GEO, then it has to be ALM. Okay, let's find X and Y given, so, all right, so I'm telling you these triangles are similar. If they're similar, then the sides have to be in the same proportion. So let's look at this. AC is with DF. So this side right here and this side are the pairs. AB and DE are pairs. So 10 goes with X as 18 goes with 12. So there's two ways to kind of do this. You can just find the scale factor, okay? So 18 to 12, well, what happens? We could just do 12 and divide by 18 and show that the scale factor is 2/3, meaning to go from this triangle to this triangle, all the side lengths are going to be 2/3 as big. So the K is equal to 2/3. If we start here and go this way, right? 18 times 2/3 gives you 12. We can also set up a proportion, which is the same thing, because if these triangles are similar, then all their sides are in the same proportion. And some people like to do that. So for this instance, let's do it this first way first and say that if 18 goes to 12 by multiplying by 2/3, then we just take 10 and multiply by 2/3 to get X. And so X has to equal then 10 times 2/3, which is 20/3, right? Which is like 6.666 repeating. Okay, so we found X that way. If you wanted to do it a different way and you want to set up a proportion, you could say that 18 is to 12 as 10 is to X. When we set up a proportion, which is totally fine. It's going to end up being the exact same thing as all of these. If you solve for proportion, we would multiply both sides by X and get 18X and multiply both sides by 12. Right? The X goes from division to multiplication and the 12 from division to multiplication, and then we would divide by 18 and get X. And then we'd realize that both of these have a factor of 6. 120 divided by 6 is 20. 18 divided by 6 is 3. And of course, regardless of what way we do, we get the same value. Okay, so we know X, meaning this side length is 20/3. Okay, let's do Y. So Y and 8 are together. Let's set up a proportion. So 18 is to 12 as 8 is to Y, because the side lengths have to be in the same proportion because the triangles are similar, and that's what it means to be similar. So we get this same idea here that 18Y equals 96 and we get y equals 96 over 18. And then, what's that, 48 ninths? And then we can divide that, both of those, by 3. Oh, can we divide 48 by 3? And it goes in what? 16 times? Yep. So then we get 16 thirds. Reducing it. And again, you could use your calculator, you could have got a decimal, but we're going to mostly work with fractions. And so now we know x and now we know y. If we wanted to do it the other way, let's think about this here for a second. If we go here and multiply by 2/3, we get all these side lengths. Well, how do we go this other direction? How do we start here and go this way? Well, how many times bigger is 18 than 12? Well, we could have looked at 18/12 and said that the scale factor the other direction is 3/2. All of these things are 3/2 times bigger, so we could have just took 8 and multiplied by 3/2 and got, we did something wrong. This y needed to be 12. What did we screw up here? That is a big issue. 96, 18. Cut it in half, cut it in half. I'm gonna have to start this whole video over again because I'm going crazy here. So this is 24. 24 over 2 is 12. So y needs to be 12. So what did I mess up here? 18 is to, I know what I did. That is ridiculous. All right, I'm not gonna start this video over. You gotta track with me. Hopefully you're like, wait a second, Lindbergh, dude, you messed this up right here and it jacked all of this up, because we know y is 12 using this method, which I guess is a good idea to leave that mistake in to show that I can do it 2 different ways, and I for sure get y is 12. So what's wrong with this? None of this, right? That was solid math, but it's worthless because the setup was wrong. I just did it too quick. Look, 18 is to 12 as y is to 8. I flipped these two, right? 18, big one, is to 12 as y. That needed to be a y, and that needed to be an 8, and that will change everything. That'll be ridiculous. So then we have 18 times 8, which is 144, excuse me, equals 12y, and then divide by 12 and get 12. And you're like, oh, that's so much better. So much better, right? Certainly it has to be 12 because it was 12 one way and the other way was wrong. So sorry about that. Remember, this math was faulty because of the faulty assumption. It does actually matter that you write the proportion correctly. So who knew? 18 is to 12 as y is to 8, and then solve the proportion. Or you can just use the scale factor idea. Again, either way you can do these. These are fun. Okay, my bad on that. You'll forgive me. Okay, are they similar? If yes, find x and y. So are they similar? And you're like, oh, check it out. They both have a right angle, and they both have this angle labeled the same. And so are they similar? Yes. Angle proves that the two triangles are similar. If the two triangles are similar, then they're in the same, then their sides are proportional, and then we can do things like finding x and y. Okay, let's try to find x first. Look at this thing labeled. This whole thing is labeled as 12, and this is 4. Well, if that whole thing is 12 and this is 4, well, that has to be 8. That's easy. That's not actually even using proportions. That's just using subtraction. But now, if I know this is 4 and I know this is 8, then I know the scale factor between the two things. I know that the scale factor is 2. 8 is double 4. This is a 3, 4, 5 triangle, so that has to be 5. And then y has to be double 5, so then y has to be 10. So y is 10 and x is 8. And if you think about it, what does this height have to be? Well, if this is 3 and this has to be 6. And what is this 6, 8? 10. Boom. Another way to show that it had to be 10. Again, what's this example? This is like a reflection or a perfect bounce. Like you took something and you chucked it at the ground and it bounces up. And if it perfectly reflects, then it's going to bounce at the same angle. Or you could even take like a mirror here and put a laser and go. The light's going to have an angle of incidence and the angle of reflection are going to be the same. So if these angles are congruent and those are 90, then the triangles are similar. If they're similar, we can find the scale factor. We found the scale factor to be 2, so everything had to be double. So we found that was 8 by just doing a little subtraction. Okay, let's move this up some. Okay, Number 4. Are they similar? Huh. Okay. Are they similar? Well, so this is 40 and this is 60 and that's 100, but that means that must be 80 because I know the triangle sum theorem. And if that's 40 and that's 80, that's 120, that must be 60. And you're like, wait a second, the triangles are the same. The angles are all the same. So we have angle, 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 which proves similarity. So yes, they for sure are similar. Why do we know? Because I just showed you that all 3 angles of the triangles are the same. So now that they're similar, their sides are in proportion. And so here we're going to have to do a little algebra. And you know what? I might move that up and grab another sheet and do a little bit of my work below this. What do you think I can do that? Make this work? All right, everyone still see the original problem. Okay, let's set up using proportions. So on this one, we have 15 is to 21. That's some ratio. 15 is to 21 as x plus 6 is to x plus 10. You see how that works? Again, I'm setting up a proportion. I can set up a proportion, and I know these have to be equal proportions because the triangles are similar, because they have angle, angle, angle. And really, again, it's just angle, angle. Okay, so now I'm going to multiply. This is division on the right side of the equation. I'm going to move it to the left side. So it's going to be 15 times x plus 10 equals 21 times x plus 6. Again, I'm just doing algebra at this point. No more geometry. Division, multiply both sides by 21 and multiply both sides by x plus 10, and now I got rid of the fraction. And now I'm going to distribute and get 15x plus 150 equals 21x plus 126. I then am going to subtract the 126 over to here and get 24. I'm going to subtract 15x over here and get 6x, and I'm going to get x equals 4. That sounds pretty cool. And we can actually figure out what these values are if we wanted to, because if once x is 4, we know that's 10, and we know that's 14. And then you can check to make sure, is 21 to 15 the same as 14 to 10? Does that ratio make sense? Meaning once x is 4, 15 to 21, is that the same thing as 10 to 14? And you can show that those are in fact the same thing. That's cool, right? That ratio's the same. And now let's do the same thing for y. So we'll do 15 is to 23 minus y as 21 is to y plus 3.2. So it must have worked out as some decimal, which is totally fine. So I had to give you some decimal here to make sure that proportion was right. Again, this side is to this side, or this side is to this side, as this side is to that side. The ratio of the side legs has to be the same. So I'm going to do the same thing. I'm going to get rid of these denominators by multiplying both sides by that denominator. Okay, effectively I'm just moving this over here and making multiplication and moving it over there, and that moving meaning I'm multiplying both sides by it. I'm going to distribute 15y and 15, I'm going to use this just to make sure I don't mess this up. 15 times 3.2 is in fact 48. And then 21 and 23 is 483 minus 21y. I'm going to add the 21y over to here and get 36y. I'm not sure if this works out. And then 483 minus 48 is 435. Oh, buddy. And then 435 divided by 36 is just some random fraction. I guess we could reduce it if we wanted to, but it's 12.083. Let's write it as a 145 over 12, which is what this is reduced is, which is really close to being 12.0, actually it is equal to 12.08 repeating. Okay, so that's what y is. So we're claiming then that y, let's just make sure we did all this right. 15 is to 21 as 23 minus y is to y plus 3.2. So 15y 48 equals 483. Let's check all this. and then minus 21, and 15. Add that over to get 36. Subtract to get 435, and then divide. Okay, that's what y is. So let's actually check to see what these values are. So 23 minus y, so that's 23 minus 1208 is going to be 10.91. And 6 repeating. And then over here, y plus 3.2. So 145 twelfths plus 3.2 is going to be 15.283 repeating. And let's see if these are in the same ratio. So let's take those. 15.283 divided by 10.916. This ratio is 1.4. Okay, the big one divided by the small one gives us a K of 1.4. Is that the same thing as 21 divided by 15? 1.4. 14 divided by 10? 1.4. So this didn't work out to some nice number. That's okay. It's a decimal. Great. But for sure, the side lengths all are still in the same ratio. Okay, this side length was 10.961 ish, reading actually, and then this side length was 15.283 repeating. All of these are 1.4 bigger than these guys. We solve them by knowing they're similar and by setting up two proportions. This one worked out nice, and this one kind of worked out messy. But again, you're not always going to get integer solutions for x and y, and you're not always going to have integer or whole number solutions for these side lengths. It's totally okay. All right, let's do the second page. Let's get rid of this. All right, back to this top. We see that now in the sheet. I think we're good. All right. So first thing, are these triangles similar? So check this out. This angle right here, see how it's shared by both? There's the little triangle, ABB, and then there's the big triangle, ACE. They both have a 90 degree and they both have this angle. So they have angle, angle. And so the answer, of course, is yes, they are similar. If they're similar, then their sides are in proportion. And so let's look at these guys. I'm going to redraw these because the little triangle is this guy. It's 8 by 6. The big triangle, oh, and y. The big triangle is 24 by x, and then this is some y plus z. Okay, so it's not the greatest triangle, but the little triangle is right here, and the big triangle, again, it's not this, that's trapezoid, it's the big triangle. The big triangle is 24 across and x up. So what's the scale factor? Well, check it out. 8 is to 24, it's 3. So we know k is equal to 3. The scale factor is 3. So 24 is 8 times bigger. 24 is 3 times bigger than 8. So x has to be 3 times bigger than 6. So we know x is equal to 18. Okay? We know y because we know the Pythagorean theorem. This is a right angle. 6, 8, that has to be 10. Okay? But if that's 18 and that's 24, then that whole thing, we can look at the Pythagorean theorem. So we could do 18 squared plus 24 squared, and then we could take the square root of it, and we could show that this whole thing is 30. But what else do we know? Well, if this is already 10, and this whole thing is 30, what's z? Well, z then has to be 20. 20, 10, 18. Not only can we show that, we can show that everything is proportional, even these two broken down. And that's something we'll get to, I think, in section 6.4. That this little piece here was twice as big as the first piece. And look, this piece is twice as big as that piece. Piece, 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 piece. Yes, 2-to-1 ratio, 2-to-1 ratio. That's not a scale factor thing, but that is a proportion that we will look up, and it is a property of similar triangles in this case. Okay, and that's all going to be due to the fact that these two lines are parallel. Okay, but for sure, the small base is 8. The big base is 24, 3 times bigger. Small height is 6. Big height is 18, 3 times bigger. Small hypotenuse is 10. Big hypotenuse is 30, 3 times bigger. All the things are 3 times bigger because the things are similar. So again, x was 18, y was 10, z was 20. The big hypotenuse happened to be 30. Okay, let's move on to the next one. So are they similar? And for the same reason, if this and this is some line, is O, N, and M, those are the coordinates, the vertices, that is their collinear, which means that that angle and that angle have to be the same. They're corresponding angles, and corresponding angles are congruent if the lines are parallel. And the same thing over here. That has to be to that. And the whole thing, the little triangle, NOP, angle O is also shared by MOQ. So little triangle, big triangle. And again, they're similar. So yes, and let's write one. So we'd say, let's do little triangle first. So triangle, NOP. NOP is similar to triangle MOQ. Okay, all right, so they're similar, and then we can use the fact that if they're similar, then the sides are all proportional. Okay, so what do we actually know here? Let's look at, again, we're going to look at this concept here in a second, but let's assume we do not know that. Let's try to find x. So this is the left side is 5. 5 is the left side of the small triangle, and then 5 plus x is the left side of the big triangle. And that has to be proportional to the right side of the small triangle, and then the right side of the big triangle is 5. This has to be a true statement. 5 is to 5 plus x, as 3 is to 5, meaning the triangles are similar. The sides are in proportion. This is me comparing the left sides, and this is comparing the right sides. Again, if this is 3 and this is 2, the whole thing is 5. If this is 5 and this is x, then the whole thing is 5 plus x. Okay, so let's solve this. So 5 times 5 is 25. And over here, we're going to multiply those two and get 3 times 5 plus x. So get 25 equals 15 plus 3x. And I get 10 equals 3x. And I get x equals 10 thirds. Again, I get a fraction. No big deal. So I'm claiming that this distance is 10 thirds. Okay? And what you can show is that not only are the sides proportional, but these segments are proportional. 2 is 2/3 of 3. 2/3 of 5 is 10/3. Like, oh, cool. It actually worked the same thing as up there because this is just like the vertical version of this horizontal thing. Okay, see how these parallel lines are vertical? These are horizontal. These sides are proportional, but then these segments, these pieces, are also proportional. 5, 2/3 of it, 10/3. So this little piece is 2/3 of that piece, just like 2 is 2/3 of 3. And so you actually could have done this easier, maybe a little quicker, and you could have just said 5 is to x as 3 is to 2. So 5 is to x as 3 is to 2, and you would have got 10 equals 3x, and you would have got x equals 10/3. See how faster that was? A little more complicated, or a little less algebra than over here, but these are saying the same thing. And again, that's my proof, is kind of how that works. Okay, so we have x, and now we're just going to find y. And y, they're not really pieces of each other. Again, this is not a mid-segment or anything. This isn't necessarily double, because this isn't intersecting in the mid-segment. Let's just use the right side and compare to the two bases. So 3 is to 5. 3 is to 5 as 4 is to y. Okay, this kind of makes sense here. 3 is the small right side compared to the big right side of 5, compares to 4 compared to the big. And so we're going to get 20 equals 3y, and we get 20/3 equals y. Cool with that? Hope so. Hope so. Hope so. Okay, so now we have x and we have y. There's y and there's x. All right, last one. I know this video is a little long. I just kind of wanted to take you through. Oh, no, we have two more. Sorry, they're kind of small. Two more here. So let's look at this guy. So I made these lines must be parallel. Well, because this is cutting a transversal, and if you can show me that these corresponding angles are congruent, then the lines must be parallel. So those are actually parallel. But again, I labeled it that way instead. You could have labeled it like this, and then you would have known those were parallel. So they have angle, angle, angle. So yes, they are similar. So how are we going to set up this proportion? Okay, this one's going to be an interesting one. If this little distance is x right here, then, and the whole distance is 9.8, can we talk that that is 9.8 minus x? That makes sense? If this whole thing is 9.8 and this is x, this has to be 9.8 minus x. And now we can set up this proportion. Okay? 14 is to 9.8 as 10 is to 9.8 minus x. I'm going to say that again. Big hypotenuse is to the big base as the small hypotenuse is to the small base. That's one way you could have done it. Okay? You also could have done big hypotenuse is to little hypotenuse as big base is to little base. Do you see how in both cases you're going to get the exact same thing? These two just switch spots, but it's the same ratio. You're still going to do 14 times 9.8 minus x equals 9.8 times 10, which of course is just 98. 14 times 9.8 is 137.2 minus 14x equals 98. 137.2 minus 98 is 39.2 equals 14x, and then I'm going to divide by 14, and I'm going to get some random decimal, which is totally okay. And I get 2.8. So x is 2.8. And you can verify this if you want, okay? If x is 2.8, then what is that? 9.8, oh, that's easy, that's just 7. Okay, so let's check this out. What I'm claiming then is that this is 7. So I'm claiming that 10 is to 14 as 9.8 is to 7. Hypotenuse is to hypotenuse as big base is to little base. If x is 2.8, then this is 7, and then you can check. You can divide it real quick. 9.7, 9.8 divided by 7, and get 1.4, and you're like, oh, cool, I did it right. They're in the same ratio, and that allowed me to find x. Okay, again, decimal is an answer, no big deal. It's going to happen. All right, the last one is really not even a problem. It's just looking through different ratios. This one is a crazy one in that there's actually 3 triangles. And we might even need a bigger paper for that. But we'll see if we can do this. Okay, so let's just kind of play around with what this all could be. Let's look at the small triangle. The small triangle has a little leg of x, a big leg of h, and a hypotenuse of d. Okay? And first of all, they're all similar to each other. Okay? The little triangle looks like this. The medium triangle looks like this, and that's this guy. This is the little leg, so h is the little leg over there, y is the big leg, and z is the hypotenuse of the medium triangle. And then the big triangle make that one bigger. This is the little leg, d. Z is the long leg, and the hypotenuse is y plus x. Again, that might take you some time to really think that one through, but there are 3 triangles there. There's this little red one here. Okay, there's that red one. There's this blue one over here, which is the medium triangle. Okay, and then you have the big triangle right here. It's like, well, I have to flip it all the way around to make it have that same orientation. So it's got a, so take this A and kind of flip it here and then set it on D. D is the bottom. And it's kind of cool how it all works out because H is the long leg in the first triangle and the base of the second triangle, which is kind of cool. Z is the hypotenuse of the blue triangle, the medium triangle, but it's the long leg of the big triangle. And so you have all these kind of crazy relationships. But again, you can write out the similarity statements if you want. You can just always start and do the short leg first. So C, D, B, C, D, B is similar to, okay, now start with the short leg, B, D, A, triangle, which is also similar to triangle. Okay, let's start with the short leg, CBA. So try to check that out. It's going to take you some time to visualize it, but similarity statements, I always just think go small to big. So start here and go the small leg, the big leg, and the hypotenuse. So CDB. And then for the medium triangle, the blue one, start here and go short leg, B, D, A. And then for the big triangle, start here and go the short leg, CBA. Okay? Ratios. There are so many ridiculous ratios you can do. You know, you could say H is to X as Y is to H, right? Or, no, let's not do that. Sorry. H is to Y as X is to H. We could write that one, right? Height is to height as base is to base. We could have said height is to height as hypotenuse is to hypotenuse. We could have said this height is to that height as this hypotenuse is to that hypotenuse. So there's a billion of these ratios. That's just one of them. Again, you're going to see this picture a lot. It's really cool because you end up with 3 similar triangles, and so all of these things are kind of related. Okay, I know this video was long. Hopefully helps you kind of get started on all those things.